How's it going, everybody? So today we're going to start taking a look at factoring quadratic trinomials, but we're going to be doing the easy ones where a is equal to 1. Many polynomials can be written in factored form just like numbers are. The reason, though, why we're going to be doing all of this factoring is because big, long polynomials, hard to solve. Short, small polynomials, easier to solve. So if we can break the big things down into the little things, we can use the zero product property and later on go and solve these a whole lot easier, okay? So a couple big things to remember. First off, we really need to remember that standard form of a quadratic trinomial is this: ax squared plus bx equals c. Okay? If it is not written in standard form already, you're going to need to rewrite it in standard form in order to do any of these factoring methods that we're talking about for today. All right? We also want to make sure that you are always looking for a GCF first. That's going to be really important. It makes things a whole lot easier. So always check for a GCF first. All right, so now we're going to start taking a look at a couple examples. Hopefully this is really more review for you guys than anything else. All right. So let me get my fancy pens. So the first one that we're going to go do and factor together is this quadratic trinomial. Quadratic because the highest power is 2. Trinomial because it's got 1, 2, 3 terms. So it's a quadratic trinomial. Okay. So what I'm trying to do is I'm trying to figure out a way to write this as the product of two other smaller polynomials. Okay. So one thing that I can do is I can look and say, all right, well, I've got this 18 here. What are possible factors of 18? I have 1 and I have 18. I have 2 and I have 9. I have 3 and I have 6. And those are pretty much all the factors that I have. Now, of those factors, I'm looking for ones that combine to give me this value of 9. Okay? So, can 1 and 18 get me 9 through adding or subtracting? No. Can 2 and 9 through adding or subtracting get me 9? No. Can 3 and 6? Sure. Positive 3, positive 6, that'll get me 9. So this is what I want to use. All right. If I go and look over at my x term, there's only two things that can be multiplied to get me x squared, and that's x times x. Okay. So when we're factoring, when we have these leading coefficients of 1, okay, we're really just having to look at this c term and asking what are factors of c that combine to this value of b. Because then I can go and write this as the product of x plus 3 and x plus 6. Okay, and this works because x times x using the distributive property will get me x squared. 6 times 3 will get me 18. And 3x and 6x will add up to 9x together. Okay, so this is the factored form of that particular polynomial. Okay, if we go and look at the next one, okay, example 2, we're going to factor x squared minus 11x plus 28. We're going to kind of go through and take a look at the same thing. Only I'm going to try and make my lines a little bit thinner. All right, so I'm going to take a look at 28, and I'm going to kind of list all the factors I can think of for 28. So I got 1 and 28. I've got 2 and 14. I've got 4 and 7, and that's about all I can think of for that number, okay? For x squared over here, it's easy. It's just x and x, remembering this has a leading coefficient of 1, okay? So, of the factors of 28, which ones are going to combine to negative 11? Well, 1 and 28 will never be 11, okay? 2 and 14, probably also never going to be 11. But 4 and 7 I could combine to make 11, but I'd have to make it where it was actually negative 4 and negative 7, because negative 4 combined with negative 7 will give me negative 11, and if I multiply two negatives together, what do I get? A positive 28. So this will factor into x minus 4 times x minus 7, okay? Now, you may recall that at the beginning we said always look for a GCF. I didn't specify that, but I just kind of glance at it. And if I'm looking at the first problem, I've got 1, 9, and 18. There's no common factors because this is 1, okay? So I can't really factor anything else besides 1. If I go and look at the second example, it's 1, 11, and 28. Again, there's no common factors. So sometimes it's obvious, and I may not mention that, but it's still something that you guys should always take a look at, okay? So hopefully you remember a lot about factoring from Algebra 1 and from geometry. If not, don't worry, you're going to get plenty of practice. But I will tell you this. If there is one skill that you have to be good at in Algebra 2, it is factoring quadratics. Pretty much the entire first semester is dependent on your ability to factor quadratics. So if you're still on the struggle bus with this stuff, you really need to take the time to come to office hours, extra help Wednesdays, whatever it takes, but you got to figure out how to factor, okay? If we go and take a look at another example, okay, this time we're going to go look at x squared minus 5x minus 24. Okay, this is again, quadratic trinomial. It's got a leading coefficient of 1. Because it's got a leading coefficient of 1, probably don't have a common factor because I got 1, 5, and 24. Not really happening. Okay, so what are my factors of x squared? Well, again, just x and x. What are all my factors of 24? Well, there's going to be a lot for this one. I got 1 and 24. I have 2 and 12. I have 3 and 8. I have 4 and 6. And then that's all the factors I got, so really only 4. But 4 is a lot. Okay, so now I have to go and ask some questions like, how can these factor pairs possibly combine to this value of 5? Okay, also remembering that this 24 is actually negative. So one of those two factors is going to have to be negative. Okay, can 1 and 24 in some way, shape, or form combine to be negative 5? No. Can 2 or 12 in some way, shape, or form using only addition and subtraction combine to negative 5? No. Can 3 and 8 combine to negative 5? Yes. Okay, if I make this a positive 3 minus 8, that will get me a negative 5. And negative 5 is what I need right here. Okay, so this is the factor pair that I'm going to end up using. All right, so I'm going to use these two to get my x's, and I'm going to use these two to get my negative 24, and the combination of those is going to give me, you guessed it, my negative 5x. So I can factor this down into x plus 3 and x minus 8. Okay? If you ever want to go through and check your factoring, just multiply it together and see if you get the original. X times x is x squared. X times negative 8 is negative 8x. Positive 3 times x is plus 3x. 3 times negative 8 is negative 24. Okay? Negative 8x plus 3x gives you 5x. Negative 24, that works. X squared, that works. So you can always go through and check your work to make sure that you're doing it correctly. All right? So we also have special cases. Okay? Special cases are where it's still a quadratic. It's still going to be written in standard form, and it's still going to probably need to have some sort of pattern or consistency with the factoring. So what we're going to be looking at first is factoring a difference of squares. Okay, so hopefully we all remember that difference is the fancy mathy word for subtraction. Okay, and squares means any number that can be or is a perfect square. Okay, so we're going to start off by realizing that these special cases, they're still standard form quadratics. The only difference is your value for b is 0. Okay, so you probably won't even see this x to the first term. Okay, it'll just be a squared term, and then it'll be some constant. Okay, kind of like example 4, where we're factoring x squared minus 16. So the long way to think about that is to rewrite it where it's in standard form with a 0 placeholder, where you write it as x squared plus 0x minus 16. And then we could go and think about it the same way we did before, where we would say, okay, well, what are the factors of x? Okay, well, I got x and I got x. What are factors of 16 that combine to 0? Well, positive 4 and negative 4, okay? Because those are inverses of each other, the positive and the negative, so they'll undo each other, so we'll end up with 0x. So you could go and factor it the old-fashioned way and say that it's x plus 4 times x minus 4, okay? Or we could go and recognize that there's something very, very special here when it says difference. And what do I have right here? A minus sign, okay? And then it says squares, okay? So this is a perfect square. 16 is a perfect square, okay? I can take the square root of x squared, and that's just x. I can take the square root of 16 because I know that's 4. So using this, I also know that it will factor into x plus 4 times x minus 4, okay? So that's the same value that we got when we did it kind of the old-fashioned way, but we went and wrote it with a 0 placeholder and we did factoring by breaking down, okay? We can also use this pattern of difference of squares and realize if it's a difference, and you can take the square root of the first term and you can take the square root of the second term, then we can express it as this square root plus this square root times this square root minus this square root. It's always going to have that opposite pattern, okay? Hopefully, you also look at that relationship and see something that is familiar, okay? Because it looks to me like we have a plus b, okay? And then we have a minus b. So what do those look like to you? Hopefully you used a magical math word. That magical math word being conjugates. Yay, conjugates. Okay, so factoring a difference of squares just uses conjugates, which you've already learned about with complex numbers. Isn't that exciting? I know. All right, so for these next two problems, these are what we're going to refer to as the challenges, okay? We are going to get to cover material like this a little bit later, but since we've already started talking about factoring quadratics where a is equal to 1 and difference of squares, this is as good a time as any to go through and start looking at these, okay? So the big thing that I want you guys to take away from seeing problems like this is that everything that we're doing is about breaking it down into smaller, more manageable pieces, okay? So if we look at this first problem, okay, I see that this actually has a leading coefficient of 2. Well, maybe that means I can take out or factor out a GCF. The other thing I'm going to notice is that it's actually a quartic function, okay? But then this is a quadratic, and then this doesn't have any variables, okay? But I still kind of see a pattern that's emerging right there. Like this is half as big a degree as this one is, which is kind of like what it is for quadratics. So maybe, just maybe, that's something that we can use to help us solve the problem, okay? So if I'm going to go and factor this, the first thing that I'm going to go through and do is factor out that GCF, okay? So I have 2, 8, and 90. Those are all even numbers, so I at the least can factor out a 2. What's left over is x to the 4th plus half of 8x squared is 4x squared, and then half of 90 is 45, okay? So now I'm going to try and factor it. But I notice that I've got exponents of 4 and 2. Okay, so maybe that's going to prevent me, or maybe things will be just fine. This is in fact a trinomial. It's got those 3 terms, so maybe I can factor it like it's a regular trinomial, like it's a quadratic, like it's quadratic style. We'll see. So first, I'm going to need to figure out if there's a way that I can use factors of negative 45 to create a value of 4. Okay, so if I start thinking about factors of 45, the first one that's jumping into my head is 9 times 5. Okay, I know that 9 times 5 is 45. Can I combine those two numbers in some way to get 4? Probably if I did positive 9 minus 5. That'll get me 4. Will positive 9 times negative 5 get me negative 45? It sure will. So I'm off to a good start. For this x to the 4th, well, I know that x times x is x squared. So does that mean that x squared times x squared will give me x to the 4th? It absolutely does. So I can say 2 is my GCF over here, and then I'm going to have one factor of x squared plus 9, so x squared plus 9, and then I'm going to have another factor of this x squared and minus 5, so x squared and minus 5. Okay, so has this been written as a series of products that when multiplied together will be equivalent to this? Yes. So guess what we just did? Factoring. Booyakasha. Okay, x squared times x squared is x to the 4th. 9 times negative 5 is negative 45. And if I combine 9x squared minus 5x squared, I'm going to get 4x squared. Check. It works. Okay. The other way that we can do that with other quadratic style trinomials is if we go and look at something like the second example here, or our second challenge, which is factoring x to the 4th minus 16. Well, this looks like a difference of squares. So maybe I can factor it like it is a difference of squares, because 16 I can take the square root of. X to the 4th, I think I can also take the square root of. Okay, so if I do the square root of x to the 4th, well, that should be x squared, because, like for my previous example, I know that x squared times x squared is x to the 4th, so that has to be the square root of x to the 4th. Okay, the square root of 16 is 4. So can I use those two values and say this could factor using the difference of squares into x squared plus 4 and x squared minus 4? Well, yeah, I think that would work. Those two are conjugates of each other. X squared times x squared is x to the 4th. 4 times negative 4 is negative 16. That works. It looks like it does anyway. But in the words of the late, great Billy Mays, but wait, there's more, because ooh, what's this? Is that a difference of squares problem inside of a difference of squares problem? That's right. It's like one of those Russian nesting dolls. That's insane. So what's the square root of x squared? X. What's the square root of 4? 2. So that will continue to factor into x plus 2 times x minus 2, but we still have the x squared plus 4. So this is written as 3 factors. Okay? But if I multiply all these factors together, am I going to get x to the 4th minus 16? I absolutely will. So the whole point of these challenge problems is really just to show you that once you have a basic understanding of how certain types of factoring work, you can expand that thinking to include other types of problems. Does it kind of fit the mold? Then use it. Okay? So, always in this math class, take the basic stuff that you know and see how you can build on it to solve newer and more challenging problems.